Okay, let's continue our discussion on renormalization group equations. So far we have looked at the equations that govern the evolution of coupling constant as you change the scale mu, okay, where mu is the renormalization scale. And also, so here, okay, and that is governed by the beta function. And note that beta function is a universal function, meaning once you have specified the theory, beta function is fixed. It doesn't depend on what you are studying, which scattering process you are studying. Okay, that's independent of those objects, those observables. It's specified once you specify a theory. And then we also looked at this gamma m, which controls the evolution of the mass parameter. Okay, somewhere here I had written yeah, here. So gamma m is this object, which is just the derivative of mr and some mu and mr factors here. And again, just like beta function, this is also a universal function, meaning it is fixed once you fix the theory. Okay, it doesn't depend on what observables you are looking at. So we had looked at these two group equations called renormalization group equations. Now let's continue further on that, and let's write down the renormalization group equations for S matrix elements. Okay. Okay, and you may recall that we have already seen that S matrix element, whether you write it in terms of bare quantities or in terms of renormalized quantities, it remains the same. So here I'm just writing that observation that we had made earlier. Okay, I'll show you in a minute where we had done that. First I write it down. Okay, I'm just making these dependencies on parameters also explicit. Okay, remember we should fix the bare parameters fixed. We should keep the bare parameters fixed so that the theory doesn't change. Okay, let me show you where we have seen this earlier. Hopefully it can go. No. Okay, I think it was in another file. So anyhow, you can go back and see that we had shown that if you write the S matrix elements in using the bare parameters or renormalized parameters and renormalized fields, okay, they have the same expressions. Okay. Now I'm going to utilize that. So the left hand side, because this is independent of mu, there is no mu here because everything is in terms of bare parameters. Mu d over d mu of S is 0. Okay, instead of writing k1 to kn, I will just write k subscript I. This is 0. Okay. Which means that mu d over d mu of the same object written in terms of the renormalized quantities is also 0. Okay, and you can turn this total derivative into partial derivatives as we did earlier. So you have mu del over del mu. Okay, this is when you are changing the mu, only mu, and then other things should change appropriately so that this relation is satisfied. Okay, so I should change, things should change appropriately with change of the, the lambda r and mr should change appropriately so that this holds true. Okay, so this is a renormalization group equation that you get for S matrix elements or any other physical observables. It will be this thing. Okay, now I want to write down the renormalization group equation for Green's functions. Okay, they will be slightly or gently more complicated. So now I want to write renormalization group equation for Green's functions. Okay, so again let's start with the bare Green's function. Okay, let me also make the m and lambda explicit. So this is 0. If you take the derivative with respect to mu, because this object doesn't depend on mu at all, okay, because this is in terms of bare objects, that derivative is 0. Okay, now recall that phi of x we had defined phi r renormalized field as z half phi. Okay, so for each field we had introduced this factor z phi half, okay, which was giving you, which was which was used in renormalizing the Green's functions. I mean, this is one of the things. You also had to bring in Zm and Z lambda. But anyhow, as far as phi is concerned, this is the renormalization constant that you have. So now I can take this equation, which is written in terms of the bare couplings and bare parameter and masses, and turn it into an equation involving renormalized Green's function. Okay, so this is Green's function with n arguments, which means you are really looking at this is a correlator involving n fields, okay, n phi's. So you have, for each phi you write a z to the half, which brings zn to the half, z to the n half, and then you have gn renormalized xn, then mr, lambda r, and now it depends on mu as well. Okay, but here when I do all this, the Green's function should be evaluated at fixed lambda and m, okay, so that I do not change the theory as I change mu. Okay, so now let's act with the derivative. So it is mu d over d mu, okay, and then it acts on z and half phi, and then you have GNR. I will suppress these arguments now, plus Z phi to the n half mu d over d mu GNR. Okay, keeping lambda and m fixed. Okay, good. Now let me define, or maybe even before that, let me write one more step. So this derivative let's take. So this will give you mu d over d mu Z phi n half, that is equal to n over 2 Z phi n over 2, okay, 1 over Z phi d over d mu Z of phi. Okay, taking this derivative will give you n over 2 and then Z to the phi n over 2 minus 1. So that minus 1 is here and the remaining Z n over 2 is here. Okay, so that's the derivative. Now I define gamma phi as Z to the phi power minus half mu d over d mu Z phi to the half. Okay, which you can check, it's same as half 1 over Z phi without a square root this time mu d over d mu Z phi. Okay, so that's definition of gamma phi. Let me box it. Okay, no, it's already here. Okay, it didn't work. So that's gamma phi. Now I will substitute this in here, okay, in this expression. So mu d over d mu Z and Z phi to the n half, I will substitute from here, okay, and then I will use the definition of gamma phi and put in this equation. So I will get then, let me, how should I do that? Okay, anyway, you can remember I'm not so good at doing this. So I'll just write it down what you will get. So you substitute the definition of gamma phi and you will get the following. So the renormalization group equation will become n, what happened? It will become n gamma phi Z phi n over 2 Gn renormalized, okay, plus Z phi n half. Okay, and then let's go back. What I'm going to do is take this total derivative and write what we had here. Okay, exactly this thing. Okay. So then you get mu d over del mu plus beta tilde del over del lambda r minus gamma m mr del over del mr. Okay, you can check that this is what you will get. And as before, you should keep lambda and m fixed. Okay, the bare ones. So what do we get? I'm just going to rearrange this slightly and you get the following. Mu del over del mu plus beta tilde delta over delta lambda r minus gamma m mr delta over delta mr plus n gamma phi. Okay, I've just clubbed everything together here. Okay, and this you have a z, this is overall factor now, z phi and half. Okay, that's an overall factor. Okay, so that's the renormalization group equation for the Green's function. Now, if you take a Fourier transform of the Gn, so Gn depends on x1, x2 up to xn, and if you do a Fourier transform of each of these x's, you will get g tilde n r. Okay, and it will also satisfy the same equation because none of these derivatives care about those Fourier transform variables. Okay, they do not get entangled with this. So, taking Fourier transform with respect to all these coordinates, okay, it will not change this equation, so we will get also the following. Because I put a tilde now, and I'm using Kn and lambda renormalized, mass renormalized, and of course mu, and that is equal to 0. Okay, so this is the renormalization group equation for the Green's function. Okay, excellent. Now we want to solve the renormalization group equations. Okay, and we are going to see some nice results which will tell us about the behavior of Green's functions at high energies. So let's look at how to find the solutions. So solution of renormalization group equation. So the equation that I have written in box, let me write it down again. Just a second. No, I will take it later. So let's do some dimensional analysis first. Okay. So I'm not doing, for some time I will not be doing any quantum field theory. I'm just doing simple dimensional analysis. Okay. There is no renormalization, nothing involved in what I'm going to do now. So I will do pure dimensional analysis. Okay, so G tilde n, okay, this is just the Fourier transform of our correlation function or the Green's function. Okay, so when you do a Fourier transform, each of these phi's become phi tilde. Okay, so G tilde n will have the dimensions of n times phi tilde. Okay, so we need to know the dimension of phi tilde. Okay, and then dimension of mass dimension of G tilde n is n times the mass dimension of phi tilde. You can put renormalized here. Okay, whether you have phi tilde or phi, they both have, whether you have phi or z, phi renormalized or phi bare, they both have the same mass dimensions because z is dimensionless. Okay. Similarly, for phi tilde renormalized or phi tilde bare, they will have the same mass dimensions. So this is n times phi tilde r. Okay. So now I will be a little bit. I will call this object as omega. Okay. And later I will put this n times phi tilde r. Or in fact, I will first write this as n d of phi tilde. Okay, so this phi tilde r, and the dimension of this I am denoting by d phi tilde. Okay, and this is what I am going to write as shortly as omega. Okay, that is the definition of omega. So let's look at this. On dimensional grounds, G tilde n r with all these arguments okay, this is equal to the following. You write f of r n. Once I have written this, it will be clear what f of r is. See, what I am saying is, if you take G tilde, okay, G tilde is a sum of certain terms, okay, and each of these terms is made out of k1, k2, kn, mr, lambda, r, mu. Okay, these are the things which enter into it, and this has to be each of the terms has to have the same mass dimension. Okay, otherwise it doesn't make sense to add objects which do not have same mass dimension. So G tilde of n is some function constructed out of these quantities k1, ki's, m's, mr, lambda, r, mu. Now if you take that quantity, if you take that expression, whatever that expression of G tilde is, and divide each of these objects, ki, see k is momentum, okay, so it has mass dimension 1. So divide it by mu. So divide each of the k's by mu. Divide mr by mu. Mr has mass dimension 1. So divide mr by mu. That makes it dimensionless. Similarly, dividing ki's by mu makes that dimensionless. So ki over mu is dimensionless. Leave lambda r untouched because lambda r is anyway dimensionless. And of course, mu divided by mu is 1. So take that Green's function. Wherever you have ki's, divide it by mu. Wherever you have mr, divided by mu. Wherever you have mu, divided by mu. Okay, that thing you get is this object fn r of these ratios. Okay, and clearly you see there is no other mu written here because mu over mu is 1. Okay, so fn r is completely dimensionless. Right, because that you have constructed out of objects that are dimensionless. Okay, so there is no way fn r can be dimension full. So left hand side is dimension full and it has dimension, mass dimension omega, right, because that's the Green's function. Okay, that has dimension omega or n times d phi tilde. So that entire mass dimension has to be taken by this factor mu to the omega. Maybe I'll give you one example and it will be clear. What I'm saying is something trivial. So think of a trivial example. Think of some function. Okay. So instead of Green's function, I am looking at just some function so that I can repeat the same argument in a simple setting. So suppose some function phi, which is a function of all these variables ki's, m, lambda, mu. Okay, I'm not writing r, it doesn't matter. And suppose this function is the following: k to the 4, let's say k1 to the 4, k1 square, k2 square, plus mu square k1 dot k2, plus m square mu square, plus lambda k2 to the 4. Okay, some expression I have constructed. All I have taken care of in writing this expression is that each dimension has each term has mass dimension 4. So that's 4, this is 4, this is 2, and this is 2. So 4, that is 4. Lambda is dimensionless in this example. So there is mass dimension 4 coming from here. Okay. Now I will write this as, so I'll do what I was saying earlier. I will divide each of the dimensionful quantities in this, which are ki, m, and mu, not the lambda, by divide them by mu. Okay. So let's write this as following: k1 over mu or 4. Okay. So I have a mu over 4 plus this one k1 over mu square, k2 over mu square. Okay, I have divided by mu to the 4, so I should have mu to the 4. Plus this one, divide mu square by mu square. It's trivial. Let's divide this one. So k1 over mu, k2 over mu. Okay, if you wish, you can divide this also by mu square, but you have to again multiply mu square. So you get mu to the 4. Okay, let's check. Mu to the 4 divided by mu square, so you get mu square k1 dot k2, same as this. Plus, again divide m square by mu square. Lambda, you don't do anything, it's dimensionless, so we don't want to touch it. Okay, so you see this I can rewrite as the following, and each term has a mu to the 4. Okay, and that has come out purely because of dimensional, because we are making everything else dimensionless, right? All the other quantities, k1s, mu's, etc., they have been divided by mu, so they become dimensionless, and that is why this is what you get. Okay, so k1 over mu dot k2 over mu. Okay, the thing in the square brackets is completely dimensionless. And the entire mass dimension of phi, which is dimension 4 because each term is of mass dimension 4, is carried by the factor mu to the 4. Okay, and that is exactly what will happen here for the Green's function. Okay, so I will be able to write it as this object, which is completely dimensionless, and the entire mass dimension will be carried by mu to the omega. Okay, so that is good. Now okay, should go to another page. Okay, let me try if I can do it. Let's see. Okay, good. It's here. Okay. Now, what I want to do is, I want to scale each of the dimensionful object here, like K1, K2, all this, by scale S. Okay, so I will scale each of these objects in the argument. So I will Ki, I will make S times Ki, okay, where S is some number like 10, 100, 1000, 100,000, whatever. Okay, and MRs also I will scale. Lambda R I will not scale because it is dimensionless. Okay, and mu of course I will scale. So I'm just scaling everything. Okay. So what do I get then? So I get G tilde N R SK1 SKN SMR lambda R S mu. So I have not touched here. This will be what? This will be S to the omega mu to the omega times Fn R. Okay, let me write the remaining things also. Okay, is this clear why it should be like this? See, this function f and r, this is made up of dimensionless objects, okay, dimensionless ratios. So when I scale ki to ski and mu to s mu, k1 over mu doesn't change, right? Because k1 is scaled to sk1 and mu is scaled to s mu. So the s cancels here. Similarly, s cancels in all of these. Also in mr and mu, because mr becomes s times mr and mu becomes s times mu. So that ratio doesn't change, and lambda r is anyway dimensionless, so nothing happens to that, okay, because we are not changing that. So when you change the scale, of all these dimensionful objects, what you get is again, so this mu to the omega f and r, that is G tilde, right? So I will just write for this object, for this product, G tilde n r k1 up to kn and mr lambda r mu. Okay, so this is how it behaves, this function behaves under scaling all the dimensionful parameters and momenta. Okay, and then the overall factor is just s to the w. Okay, so this thing times s to the w. Okay, very good. So now just remind you, I have not done any renormalization group equations. Okay, I am just doing dimensional analysis. Okay, I am just counting dimensions and looking at how these functions behave when you change the scale. Okay, and whatever is written here is only on dimensional grounds. There is no renormalization, no field theory entering into this. Okay, whatever I have said could have been said in some other course where you are not doing quantum field theory. Okay, so now let's do one thing. We should let's differentiate this with respect to s. Okay, so differentiate this result with respect to s. So I will get a differential form of this. So S d over ds of g tilde n r s ki, okay, instead of writing n times, I'll just write s ki m r lambda r mu is equal to omega s to the omega. So I'm differentiating this, but then you have another s multiplying, so omega s omega minus 1, but then because you have s multiplying, it gives you again s omega g tilde n r something went wrong. No, everything is fine. Yeah, I wanted to write one more step before differentiating, so let me do that. Okay. So this is this. From here I can also write s of ki mr lambda r mu. So what I'm doing is, this is here, okay, this I'm calling mr prime, this I'm calling mu prime, okay. So for a moment you read it as mr prime mu prime, okay. So mentally you read it as mr prime mu prime, and this is s to the w g tilde n r ki's. Then if this is mr prime, then this is mr prime divided by s, right? There is a factor of s between the two. So now I'm, instead of calling that mr prime, I'm calling it mr. So this will be mr over s, okay. Then lambda r, nothing happens to that, and this is mu prime, okay. So this is mu prime over s, and I'm calling mu prime as mu again. Okay, so that's the relation. So you have a Green's function here, which is having momenta which are all scaled up by factor of s, but the masses and other parameters are still fixed, okay, and they are related to the Green's function with these momenta unchanged, unscaled momenta, by this relation where you see that the mass parameter and the renormalization scale, they are scaled down by a factor of s, okay. Okay, so now let's differentiate this with respect to s, and still remembering we are still doing purely dimensional analysis. So I'll differentiate this with respect to s. Come on, see. Let's hope it works. Yes. Okay. Now let's differentiate this. Okay. So what does that give? That gives s d over ds. Okay, so I'm differentiating with respect to s and then multiplying s also. G tilde n r s ki m r lambda r mu. This is equal to omega s omega. I have already explained why you'll get this thing. G tilde n r Ki mr over s lambda r mu over s. Okay. Okay, let me write down the answer and then I will explain. Plus s to the omega minus mr del over del mr g tilde nr ki mr over s lambda r mu over s. And then you'll have one more term, which is s to the w minus mu del over del mu, okay, acting on, here also I could have written like this to be symmetric. So g tilde nr, and again the same thing. Let's see if it is all correct. Yes, omega. Okay. I will tell you in a moment, but let me just club everything together. So this is omega, and you remember what omega was? Omega was the dimension of gr, okay, which is n times dimension of phi tilde. Okay. So omega minus mr delta over delta mr del over del mr minus mu del over del mu acting on g tilde n r ski ski mr lambda r mu. Let me tell you why. See here, g tilde n with this scaled up k, but all these other parameters without scaling is related to this one by s omega. Related to this factor, related to this g tilde with this overall factor multiplying. So here you see you have s omega multiplying exactly this quantity. In here also s omega, s to the omega multiplying exactly this quantity, and similarly here. So you get this factor in each of the term, and that is what I have collected into the left hand side of this. Okay, so that's why you have gn, ski, mr, lambda r and mu, and not mr over s and mu over s. Okay, it's just I have used this relation here again. Okay, so this is what we get. Let me again rewrite this with bringing all the terms on the same side, and I will also write the renormalization group equation which we have written down earlier. So I'll put them all side by side so that we can work with them later. So here, okay, let me write here and then copy paste. So you get s d over ds plus mr del over del mr plus mu del over del mu minus omega acting on g tilde r, g tilde n, ski mr lambda r mu equal to 0. Okay, so what is this equation telling you is how this Green's function evolve when you scale up the external momenta, okay, and leave everything else unchanged. Okay, that is the, leaving everything else unchanged, meaning keeping the bare quantities are always fixed, right? Because we are not changing the theory. So that's the equation we have got completely based on dimensional analysis. Okay, before proceeding further, let me just tell you how you get all these terms. So what we have done here is we have when you are differentiating with respect to s, okay, this part was simple, but when you are differentiating with respect to s, you can trade off that differentiation with respect to s to a differentiation with respect to mr, right? Because this always comes in this product, mr over s. So when you are differentiating with respect to s, you can change that differentiation with respect to s in terms of a differentiation with respect to mr. And similarly here, instead of differentiating with respect to s, you can turn the differentiation into a differentiation with respect to mu. And this should be something familiar. I can just show you here. So if you have some function f, which is, let's look at this part, okay, and we want to differentiate with respect to s, okay. So this is del f z over del z into del z over del s. What is z? Z is m over s, m over mu. Okay, I should have used s. Let's write it as m over s. M over s. This is s. Okay, so now you can write del over del m f m over s as del f over del z into del z over del m. Okay, so derivative with respect to s, let's write down that thing. So del over del s f m over s is this object, del f over del z into del z over del s. Okay, this is the same equation I have written, which is, I can write this del f over del z as, I will just take this thing and multiply with the inverse. Okay, multiply with the inverse of del z over del m on both sides. That gives you del f over del z, and I will just substitute it here. So you get del over del m of f or m over s times del z over del m inverse times del z over del s. Okay, and you can see that del z over del m is 1 over s, and del z over del s is minus m over s square. Okay, so here you get this product becomes minus m over s. So you get del f over del s of f in when you change that in terms of this derivative with respect to m, you get minus m over s del over del m f of m over s. Okay, that is what I have used. So you see, taking derivative with respect to s, when you have mr over s, will give you minus mr over s times this derivative with respect to m. So here you see minus mr over s, you will get and a derivative with respect to mr, but that mr over s, you have to also multiply this s, this explicit s, and which just kills that one. And similarly for this. Okay, you turn the derivative with respect to s into a derivative with respect to mu. So that is how I have written down these two terms. Okay, so that was our dimensional analysis. I will just copy this equation and because we are going to use it again. Command C. Okay, so I'll also bring the other equation which we had gotten from renormalization group. Where is that? Here. Okay, so this is equal to 0 from RG. Okay, and this is from dimension analysis. Okay, I just want to clean up a bit. Okay, good. So we have these two equations now, and each of which has a mu del over del mu. Okay, so we can now eliminate this derivative with respect to mu, and let's see what we get. Okay. So we get S d over ds minus, I'm taking, okay, let me just write beta tilde del over del lambda r plus 1 plus gamma m mr del over del mr minus n d phi tilde. Okay, instead of omega I am writing n d phi tilde. Okay, because that is what omega was, plus gamma phi Okay, this is what you get when you eliminate mu. Okay, we'll work with this equation in the next video, but here you can note that this is the dimension of phi tilde, okay, and you are getting this gamma phi together with it. Okay, and similarly here 1 is the, I mean this is just mr, right? If gamma m was not present, then it would have been just mr. Now you have that shifted to mr gamma m. Okay, so these are what are called anomalous quantities. So this gamma phi is called anomalous dimension. Okay, this gamma phi would be 0 if you do not have any if you don't have to renormalize, right? Because remember, this gamma phi is coming from the derivatives of z. Somewhere here I should have it. Here. Okay, so if z phi is 1, if you don't have to renormalize, there are no infinities, z phi is 1, okay, then this derivative will give you 0, okay, and gamma phi is just 0. Okay, and similarly for the gamma m, it will also be 0. So you see, in the absence of renormalization, in this equation you will not have gamma n and gamma phi. Okay, and that is why they are given this name, anomalous dimension. So gamma phi, we call it as anomalous dimension. Okay. So our goal will be to solve this equation, because when you solve it, okay, that's a differential equation, you solve it and you can write then g tilde n as function of ski with all these things here in terms of g tilde n of ki. Okay, so you will use a boundary condition and put, let's say you choose boundary condition to be s equal to 1. Boundary to be s equal to 1. So you will be able to relate Green's function with scaled up momenta to a Green's function without scaling of the momenta. Okay, and that is what we will do next. So we'll see in the next video.